Greetings everyone. My name is Dhruv Kumar Vyas. I am a first year BTech ICT student at Marwadi University, and this is my submission for the BW simulation project, the car battery voltmeter. Now let us have a glimpse of all the topics that we'll be covering in this video. Firstly, we'll be learning some basics of a voltmeter, like what is a voltmeter, how is it used, and what is a car battery voltmeter. Then we'll be learning some basics of a car battery, like what is a car battery, why is it used, its working principle, its construction, its electrical parameters, and the relation of voltage and the energy level of a car battery. Then we'll be moving on to the final segment of this video, the circuit explanation and its working, where we'll be covering topics like overview of the circuit, individual parts of the circuit, component list, what is an op-amp, working of an op-amp, the LM324 op-amp, Zener diode voltage regulator, voltage divider, output, and the final simulation. So now let us move on to the first segment of this video, voltmeter basics. Now let us understand what is a voltmeter. Well, a voltmeter is an electrical instrument used for measuring electric potential difference, that is voltage, between 2 points in an electric circuit. Here we'll be using the voltmeter specifically to measure the voltage of a car battery, hence the name car battery voltmeter. It has a very high resistance, which means negligible current flows through the voltmeter. Mainly, there are two types of voltmeters. One is analog type and another one is digital type. This image shows an analog voltmeter, whereas this image shows a digital voltmeter. Actually, this image shows a multimeter. A multimeter can measure various electrical quantities like voltage, current, and resistance. Also, voltmeters can be used to measure two types of voltages, AC voltage and DC voltage. As a car battery is a DC voltage source, we'll be using a DC voltmeter. So now let us learn how a voltmeter is used. A voltmeter is connected in parallel to the 2 points in the circuit where we want to measure the voltage, in our case the car battery. The positive probe of the voltmeter, which is red colored, is connected to the positive terminal of the car battery. And similarly, the negative probe of the voltmeter, which is black colored, is connected to the negative terminal of the car battery. Here, as seen in this image, the technician is measuring the voltage of a car battery by connecting the positive red colored probe of the voltmeter to the positive terminal of the car battery, and by connecting the black colored negative probe of the voltmeter to the negative terminal of the car battery. We are connecting a voltmeter in parallel and not in series because we want to measure the potential difference across 2 points. Let us move on to the next segment of our video, the basics of a car battery. In our lives, we have used numerous types of batteries. But what specifically is a car battery? Well, a car battery is a rechargeable battery that is used to start a motor vehicle, that is, a car. Its main purpose is to provide an electric current to the electric powered starting motor, which in turn starts the chemically powered internal combustion engine that actually propels the vehicle. But that's not the sole purpose of a car battery, to start the vehicle. Once the engine is running, the battery runs the car's electrical systems like headlights, AC, radio, and other facilities. Now, let us understand the working and construction of a car battery. A car battery is made from lead and lead oxide plates, which are submerged in dilute sulfuric acid. A car battery is basically an electrochemical cell which converts chemical energy into electrical energy and also stores it. The anode or the positive terminal of the car battery is made from lead oxide plates, and the cathode or the negative terminal is made from pure lead plates. As a car battery is made primarily from lead and acid, it is also known as a lead acid battery. In this image, it can be seen that this battery is labeled a lead acid battery. So now let us look at some of the electrical properties of a car battery. A car battery is generally rated at 12 volts and 50 to 100 amp hour. Now, we all know that amp hour is a unit of energy. So, the amp hour rating of a car battery represents the energy storage capacity of the battery. A higher amp hour rating shows a greater energy storage capacity. The more the amp hour rating of the battery, the more energy the battery can store and the longer it will run. Now, let us clear one thing. Even though a car battery is rated at 12 volts, the voltage of a fully charged car battery is not 12 volts, but is generally between 12.6 to 13 volts. As it can be seen from this image, the voltage of this fully charged car battery is not 12 volts, but 12.6 volts. Now, let us understand the relation of the voltage and energy of a car battery. Our circuit is based on this concept, so it is very necessary to understand this concept. By measuring the voltage of the car battery, we can calculate how much energy is remaining and how much the battery is discharged. As it can be seen from this table, which shows us the relation of battery voltage and energy level in percentage, a car battery whose voltage is 12.6 or higher is said to be 100% charged. A car battery whose voltage is near about 11.45 volts is 75% charged and 25% discharged. Now we enter the danger zone. If the car battery whose voltage is near about 10.2 volts, then the battery is said to be 50% charged and 50% discharged. And if the battery voltage is near about 9 volts, then the battery is dead. It is fully discharged. So now let us move on to the most exciting segment of our video, the car battery voltmeter circuit. This is the circuit diagram of the car battery voltmeter circuit that we are going to make. Now, at first sight, the circuit might seem very difficult. We've got a lot of resistors, many op amps, Zener diodes, and LEDs. But believe me, the circuit is very easy to understand. And further, we'll see breakdown of this circuit into three different parts. This is the list of components that we are going to use to make our circuit. As I mentioned earlier, if we look at the whole circuit together, then it might seem very difficult and hard to understand. But if we divide the circuit into three segments, its working becomes really easy to understand. Our circuit is mainly divided into three parts. The first part is a 5.1 volt voltage regulator made using a Zener diode and a series current limiting resistor. The second part is a voltage divider which will provide us with reduced car battery voltage and some reference voltages against which our reduced car battery voltage will be compared. And the last part is the comparator and the output, which is made from op amp, some LEDs, and current limiting resistors. Now, as I said that our circuit is made using op amps, a question might arise in your mind, what is an op amp? Well, in our circuit, the op amp serves as the brains of the circuit. So, it is very necessary to understand the functioning of the op amp. So, let's start from the basics. What is an op amp? Well, simply put, an op amp is a very high gain DC amplifier. But what's an amplifier? An amplifier is any electronic device that can increase the magnitude of peak to peak voltage of any signal, either AC or DC. Now, as it is mentioned here that op amp is a DC amplifier, it can amplify both AC signals as well as DC signals. It is also written that an op amp has a very high gain. But how much high? Well, theoretically, an ideal op amp has almost an infinite gain. But in real life, the op amps have a gain of almost 10 raised to 5 to 10 raised to 6, which is also very high. Also, an op amp has very high input impedance, meaning no or negligible amount of current will flow through its inputs. Also, it has a very low output impedance, so it will provide very low resistance to the flow of current at its output. A basic op amp has mainly 5 pins. As seen in this figure, it has one positive power supply which is marked as plus VCC. It has a negative power supply pin which is marked as minus VEE. It has two input terminals. One marked with plus is the non-inverting input terminal and the other marked with minus is the inverting input terminal. Lastly, an op-amp has one output terminal. In open loop configuration, that is, when no feedback is given from the output terminal to the input terminals, in that case, the op-amp acts as a differential voltage amplifier, meaning the output voltage of the op-amp will simply be A times V2 minus V1. What is A? A is the open loop gain or the characteristic gain of an op-amp. V2 is the voltage applied at the non-inverting input terminal and V1 is the voltage applied at the inverting input terminal. So the output voltage is simply the difference of the voltages applied at the input times the gain. Now let us understand the working of an op-amp. As discussed earlier, the open loop gain of an op-amp is nearly infinite. So in open loop configuration, if the voltage at the non-inverting input terminal is greater than the voltage at the inverting input terminal, then the output will be saturated and will get the maximum positive voltage that we have applied to the op-amp. As seen in this figure, we have connected a maximum positive power supply of 15 volts and a maximum negative power supply of minus 15 volts to this op-amp. At the non-inverting input terminal of this op-amp, we have applied 12 volts and at the inverting input terminal, we have applied a 5 volt supply. So it is clear that the voltage at the non-inverting input terminal is greater than the voltage at the inverting input terminal. So as seen from this oscilloscope connected to the output is saturated and we are getting the maximum positive power supply that we have connected to this op-amp, that is plus 15 volts. Thus, if V1 is greater than V2, then the output voltage is equal to plus VCC, that is our maximum positive power supply. And if the voltage at the inverting terminal is greater than the voltage at the non-inverting terminal, then in this case also the output will be saturated. But in this case, we'll get the maximum negative power supply voltage at the output. As seen in this figure, we have connected 5 volts to the non-inverting input terminal and 11 volts at the inverting input terminal. So clearly the voltage at the inverting input terminal is greater than the voltage at the non-inverting input terminal. So as it can be seen from this oscilloscope, the output is saturated and we are getting the maximum negative power supply voltage at the output. Thus, if V2 is greater than V1, then Vout is equals to minus VEE. Thus, in open loop configuration, the op-amp acts as a voltage comparator. Thus, it compares the two voltage at the non-inverting and the inverting input terminal. We can get the output according to the set voltage conditions at the input. In this circuit, we'll be using the LM324 quad op-amp IC. Basically, it has 4 operational amplifiers embedded in one package, hence the name quad op-amp IC. This IC has 14 pins. Now, let us understand the working of this circuit in detail. The first part of the circuit is the Zener diode voltage regulator. This part of the circuit will act as a constant voltage regulated power supply which will provide us with 5.05 volts, that is almost 5.1 volts thanks to this Zener diode, the 1N4733A. Here the 1N4733A Zener diode, which is a 5.1 volt Zener diode, is connected in reverse bias with the battery through a series current limiting resistor of 1.2 kilo ohms. Here, the reverse bias voltage applied across the Zener diode is greater than the Zener breakdown voltage of this diode, which is 5.1 volts. Thus, for all supply voltages greater than 5.1 volt, we will get a constant 5.1 volt output at this node, which can be seen here. Here, it is important to note that the voltage of the car battery, even when fully discharged, will not go below 8.5 volts and certainly not to 5.1 volts. Thus, there will always be a reverse bias voltage of 5.1 volts across the 1N4733A Zener diode. So, for any type of battery, either charged or discharged, we will always get a 5.1 volts reference. Now, let us look at the voltage divider part of our circuit. Here, we are using two voltage dividers made using resistors. The first voltage divider, made from resistors R1, R2, R3, and the potentiometer R4, is connected across the 5.1 volt reference and the ground. This 5.1 volt reference is the same that we are obtaining from the Zener diode voltage regulator. The second voltage divider, made from resistors R5 and R11, is connected across the supply, that is, the car battery and the ground. Let us move on to learn about the first voltage divider. This voltage divider will provide different reference voltages against which our reduced car battery voltage will be compared. The different reference voltages obtained from this voltage divider will be connected to the non-inverting input terminals of the respective op-amps. The 10 kilo ohm potentiometer is used to control the reference voltages. It is generally kept at 50%, so 5 kilo ohms. Here, the output voltage of the Zener diode voltage regulator that is connected here is constant. Thus, the reference voltages thus obtained will also be constant. As it can be seen, we are obtaining four reference voltages from this voltage divider. The first reference voltage is 5.04 volts, that is almost 5.05 volts. Second is 4.56 volts. Third is 4.07 volts. And the last and fourth one is 3.58 volts. The VREF1 is connected to the inverting input terminal of the first op-amp U1A. The VREF2 is connected to the inverting input terminal of the second op-amp U1B. The VREF3 is connected to the inverting input terminal of the third op-amp U1C. Lastly, VREF4 is connected to the inverting input terminal of the fourth op-amp, that is U1D. Now, let us look at the second voltage divider made from resistors R5 and R11. This voltage divider will provide us with a reduced battery voltage, that is 2 by 5 times the battery voltage. This reduced voltage will be applied at the non-inverting input terminals of all the op-amps. The calculation for the voltage divider can be seen here. Finally, let us understand the output stage. The output stage consists of 4 op-amps and some LEDs. The plus VCC of all the op-amps are connected to the anode of the car battery, and the minus VEE of all the op-amps is connected to the cathode of the car battery. Non-inverting input terminals of all the op-amps which are marked with plus are connected to the reduced car battery voltage obtained from the second voltage divider. The inverting input terminal of the first op-amp is connected to VREF1, second to VREF2, third to VREF3, and the fourth to VREF4. The output of all the op-amps are connected to LEDs with series current limiting resistors of 1 kilo ohms. So that's the end of all the concepts that we needed to learn to understand the working of this circuit. We have covered A to Z all the topics that are necessary for understanding the working of this circuit. Finally, let us see the circuit in action. Now, let us simulate the circuit. Initially, I have kept the battery voltage at 13 volts. Here, at the output, all the LEDs are on, and the green LED is the last LED which is on. This indicates that the battery is 100% charged. Now if I reduce the car battery voltage to around 11.4 volts, Then as you can see that the green LED turns off and the last LED to be on is the yellow LED. This indicates that the battery is 75% charged and 25% discharged. Now if I reduce the battery voltage to 10.2 volts, and as you can observe that the yellow LED turned off and the orange LED is the last LED to be on. This indicates that the battery is 25% charged and 75% discharged. Now if we reduce the car battery voltage to around 9 volts, then as you can see that the orange LED turned off and the red LED is only on. This indicates that the battery is fully discharged. This brings us to the end of the video. In this video, we learned all about a voltmeter, a car battery, and also the car battery voltmeter circuit and its individual parts, and finally how it works. At last, we also saw the simulation for the circuit. So hope you liked this video and learned something new. Please consider liking this video and sharing it with your friends.